Diversification is a cornerstone of modern portfolio theory, but it fails exactly when you need it most, during market crashes. This episode dissects the mathematical machinery behind that failure, including Copula tails, strategy gradient variance, and more. We explore why robust frameworks beat complex models in AI-driven quant finance. Reinforcement learning in trading often uses the reinforce algorithm, which estimates policy gradients from sample trajectories. The naive estimator has variance that grows with the square of the trajectory length. For high-frequency trading with over 1,000 steps, the gradient becomes pure noise, rendering learning ineffective. A simple baseline, subtracting a constant, can reduce variance by orders of magnitude, making training feasible. However, the optimal baseline is not the average return, it is the conditional expectation of the return given the state. This is why value networks are standard in PPO and A2C algorithms. By using a state-dependent baseline, the gradient estimator has much lower variance, enabling stable learning in complex trading environments. The variance of the gradient estimate in policy gradient methods depends on the baseline choice. Minimizing that variance yields a weighted conditional expectation of the return, where the weights are the squared norm of the score function. This is not the average return, it is state-dependent. The optimal baseline reduces variance by accounting for the specific state's influence on the return. This derivation is crucial for understanding why value networks are used as baselines in modern algorithms. It shows that a constant baseline is suboptimal, and a state-dependent baseline is necessary for efficient learning. This insight is fundamental to the design of stable reinforcement learning algorithms for trading. Without a baseline, the variance of the gradient estimator grows quadratically with the number of steps. This is because the return accumulates over time, and the product of gradients and returns compounds the noise. In long-horizon tasks like trading, this quadratic growth makes the gradient signal vanish in noise, preventing learning. With a value baseline, the variance grows only linearly, making training stable for long horizons. This linear growth is manageable and allows the algorithm to extract useful signal even from long trajectories. The contrast between quadratic and linear growth highlights the critical role of baselines in reinforcement learning for financial applications. Traditional factor models fix the number of factors, like Fama-French's 5. This fixed structure can be too rigid for capturing the dynamic nature of financial markets. Bayesian nonparametrics, using the Indian buffet process, lets the number of factors grow with data. The expected number of factors scales logarithmically with the number of stocks. This automatically prevents overfitting in small samples and captures more dimensions in large ones. Empirical studies on U.S. equities find that IBP models infer 10 to 20 factors, far fewer than PCA's 50 to 100, yet with comparable explanatory power. This suggests that a parsimonious set of factors can explain returns as well as a larger set, reducing the risk of overfitting. The Indian buffet process assigns a binary matrix indicating which stocks are exposed to which factors. Each stock may be exposed to multiple factors, and the matrix is learned from data. The expected number of active factors grows logarithmically with the number of stocks, ensuring the model adapts to data size. This property is desirable because it prevents the model from becoming too complex when data is scarce, and it allows for more factors when data is abundant. The IBP prior is a key component of Bayesian nonparametric factor analysis, providing a flexible yet controlled way to model latent structure in financial returns. Copulas model the dependence structure between assets. The lower tail dependence coefficient measures the probability that one asset crashes given another crashes. For multivariate normal, this is 0, implying independence in extremes. But financial assets exhibit asymptotic dependence in downturns. Student-T copulas capture this with a positive tail coefficient that increases as degrees of freedom decrease. During the 2008 crisis, tail dependence across asset classes jumped from 0.1 to 0.2 to 0.6 to 0.8, meaning correlations approached 1 in extreme moves. This dramatic increase in tail dependence during crises is why diversification fails. Assets that seem uncorrelated in normal times become highly correlated in crashes, undermining the benefits of diversification. The lower tail dependence coefficient is the limit of the conditional probability that one variable is below its quantile given the other is. For Student-T copulas, it depends on the degrees of freedom and correlation. As degrees of freedom go to infinity, it approaches zero, the normal case. This coefficient quantifies the likelihood of joint extreme losses. In finance, a positive tail dependence means that during market crashes, assets tend to move together, reducing diversification benefits. Understanding this coefficient is essential for risk management, as it provides a more accurate measure of tail risk than simple correlation. Traditional mean variance optimization uses Pearson correlation, which underestimates tail risk. A portfolio with correlation 0.3 can behave as if correlation is 0.9 in a crash. This is because correlation measures average dependence, but tail dependence captures extreme co-movements. Tail dependence is the true measure of diversification benefit. Ignoring tail dependence can lead to portfolios that are over-diversified on paper but under-diversified in practice during market stress. By incorporating tail dependence into portfolio construction, investors can better protect against extreme losses and achieve more robust diversification. Wasserstein distance measures the cost of transforming one distribution into another. In asset allocation, minimizing the Wasserstein distance between the portfolio return distribution and a target distribution automatically penalizes fat tails. This is because heavy-tailed assets deviate more at extreme quantiles. Surprisingly, if the target distribution is also fat-tailed, like a crisis scenario, the allocation shifts back toward those assets, as their tail shapes match. This reveals a deeper philosophy: there are no inherently good or bad assets, only matches to the target. This approach provides a flexible framework for tailoring portfolios to specific risk preferences, especially in extreme scenarios. For one-dimensional distributions, the 2-Wasserstein distance has a closed form involving the inverse CDFs. This makes it computationally tractable for asset allocation. The closed form allows for efficient optimization of portfolio weights to match a target return distribution. By using this metric, investors can directly control the shape of the portfolio's return distribution, including tail behavior. This is a significant advantage over traditional mean variance optimization, which only considers mean and variance. The tractability of the Wasserstein distance enables its practical use in quantitative finance, providing a powerful tool for distributional targeting. In continuous time market making, the optimal bid-ask spread is not symmetric. The market maker's inventory and the presence of informed traders force dynamic adjustments. The Hamilton-Jacobi-Isaacs equation governs the value function. With inventory aversion, the market maker skews quotes, holding a long position lowers the ask to encourage selling and raises the bid to discourage buying. When informed traders are present, the spread widens to compensate for adverse selection. Sometimes the optimal strategy involves deliberately quoting unfavorable prices to flush out informed traders, a form of signal jamming. This highlights the complexity of market making and the need for sophisticated dynamic strategies. The market maker's value function satisfies a Hamilton-Jacobi-Isaacs equation, where the optimal quotes are chosen to maximize expected utility while accounting for inventory risk and order flow. This equation provides a rigorous framework for determining optimal bid and ask prices in real time. By solving the HJI equation, market makers can dynamically adjust their quotes to manage inventory and mitigate adverse selection. This approach is essential for automated market making in modern electronic markets, where speed and precision are critical. The HJI framework allows for the incorporation of various risk preferences and market conditions, making it a versatile tool for quantitative trading. Transfer entropy measures nonlinear predictive information from one time series to another. For Gaussian processes, it is equivalent to Granger causality. In financial data, transfer entropy values are tiny, typically 0.001 to 0.01 nats, indicating that nonlinear causal effects are extremely weak. Linear Granger causality accounts for 70 to 90% of the transfer entropy. This explains why simple linear factor models often outperform complex nonlinear ones out of sample. Nonlinear patterns are easily overfitted to noise. The weak nonlinear causality in financial markets suggests that the marginal benefit of complex models is limited, and simpler models are often more robust. Transfer entropy from Y to X is the conditional mutual information between Y_t and X_t plus 1 given X_t. It measures the reduction in uncertainty about X's future from knowing Y's past. This definition captures both linear and nonlinear predictive relationships, making it a general measure of causality. In practice, estimating transfer entropy from financial data requires careful statistical methods due to the low signal-to-noise ratio. The small values observed in financial markets indicate that nonlinear predictive relationships are weak, supporting the use of simpler models in many applications. These mathematical facts paint a sobering picture. Financial markets have extremely low signal-to-noise ratios, weak nonlinear structures, and underestimated tail risks. The real progress in AI-driven quant finance lies not in inventing ever more complex models, but in designing robust frameworks that resist these mathematical traps. Use Bayesian nonparametrics to control model complexity, copulas to manage tail risk, optimal transport to calibrate distributions, and HJI equations to guide dynamic strategies. That is the mark of professional competence. We read every comment. Markets reward discipline, not certainty. If this analysis helped, like the video and subscribe to DeepQuant. Tell us in the comments which market idea we should test next. Evidence beats noise. Control risk before chasing returns.